Hello, my name is Quinn Kaibartis, and today I'll be talking about our work into the development, implementation, and evaluation of a force dynamic model of narrative agents for emergent narrative works. When we think about emergent narrative works, we often think of the large, complex, deep simulations of games such as Dwarf Fortress or the Crusader Kings or Sims franchises. We think of decades of development, interwoven databases of rules, and of course, that the workings of these great machines will eventually produce memorable moments of narrative. Except often they don't. Often the narrative in these games are dull, repetitive, or downright strange. The solution often is that more systems are built, more rules are authored, or the developers rely on artificial systems such as drama management, curationism, or mediation of the simulation events. In our research, we opted to take a different approach, one which aims instead to understand the implicit behavior of a small set of rules and their immediate reaction to the environment, taking inspiration instead from emergent systems such as the Boyd's flocking algorithm or Conway's game of life. In particular, we aim to create a model of narrative agents which enable the system to act as a generator of conflict curves, namely, moments of rising and falling conflicts that occur periodically. Our work is based upon Talmy's concept of force dynamics, which imagines a semantic model controlled by simple physical forces of a protagonist acting against an antagonist. This work also builds off of our previous work into modeling emergent narratives using possible worlds. In such a model, each character is composed of a set of possible worlds representing the ideal states of the actual world that the character desires. The characters take actions to make the actual world match the ideals of each of the possible worlds, and the difference in the character's internal or interpersonal ideals leads to situations of conflict, the navigation of which forms a narrative. While the full details of the possible worlds model are outside the scope of the paper, we can summarize as follows. We have an actual world which assigns truth values to a set of propositions that indicate everything that can be true in a world. Each character has a set of themes or worldviews which, when provided the state of the actual world, return a value representing the conflict or satisfaction of the character with the state of the actual world. The goal of each character is to reduce their conflict to zero for each theme by taking actions to change the truth values of the actual world. Our force dynamic model keeps the same approach as the possible worlds model, but instead characters act by moving within an abstract space representing the conflict space formed by each character's themes. Action selection is done by selecting the action whose movement most closely matches the movement in the abstract space. Each character's movements are controlled by four main behaviors. The first is a gravitational force which always pulls a character towards a point of zero internal conflict, meaning in the absence of other forces, a character will take actions to reduce their own internal conflict. The second is an interpersonal force, which is a reaction force, that says that an agent will react to any movement caused by the actions of another agent by attempting to cause that same movement back to the second agent. This force is cumulative. An example of this is that helpful actions will cause the character to react also with helpful actions, and conflicting actions will cause the desire to conflict further. The third behavior says that witnesses who observe an action will receive the impact of an action, as well as the corresponding changes in the interpersonal force, but at a reduced strength. Lastly, the fourth behavior says that, while the gravitational force is constant, the interpersonal force will decay for each time step according to a coefficient of friction. The resulting system was implemented in the Unity game engine, and a Python script was used for visualization. A visualization user interface was developed that allows authors to simulate an emergent narrative work and analyze the results, including the textual output, the conflict curve, which can also be viewed for each character, as well as large amounts of summary information, such as the average relationship between characters, or a live modification of the witness scale or the friction coefficient. Actions are edited using two plain text files. The first uses a simple scripting language to author the action, its preconditions, and outcomes. The second is a simple grammar that allows the actions to be realized as text. In this way, it is easy to author new actions and visualize their impact on the simulation immediately. The conflict curves for each character are exported after a run of the simulation, which allows the conflict curves of each character to be seen simultaneously. For the experiment, given that our system embeds a quantifiable level of conflict, we want to test and observe according to the desirable properties of conflict curves. This means we want to see regular rising and falling of conflict over time. We wish to see characters either support or hinder each other, mainly caused by the interpersonal forces, and we want the system to be dynamic, with conflicts being different and avoiding stagnancy, repetitive actions, or high volumes of noise. We created a testbed world designed to emulate a set of negotiations in a fantasy world. This testbed has 3 propositions, 3 themes, 9 characters, and 60 actions. We want to test the system according to 2 variations. Given that our system is discrete, we test 2 forms of character selection procedure, given that at each time step one character takes 1 action. The first is a discrete round-robin selection, and the second is a random selection of 1 character to act per time step. More importantly, we test 3 different action selection procedures. The baseline is a greedy action selection where each character simply aims to minimize their overall conflict, irrespective of their relations to the other characters. Second, we test the force dynamic model, but with all interpersonal forces fixed at 0, to understand the impact the interpersonal forces play on the overall system. And lastly, we test with the force dynamic model as intended, with interpersonal forces and a fixed witness scale and friction coefficient. Each simulation was run for at least 150 time steps, with some simulations being given extra time to better observe certain late simulation behavior. Considering first the results for the greedy model, we found that there was an overall stable downward trend of conflict, with only minor rising and falling action. Notably in this, and all results, the deterministic round-robin character selection procedure hits a stable cycle, where the characters begin performing the same actions endlessly. In the force dynamic model without interpersonal forces, the same downward trend is visible, but this time with almost no rising or falling action. The reason for this is when the interpersonal forces are set to 0, characters aim not only to improve their internal conflict, but to do so without causing any change to the other characters. In the model as intended, we find the opposite results to the first 2 tests. The overall trend is for conflict to grow over time, showing the regular rising-falling behavior we intended with far greater variance. Though outside the scope of this work, tweaking the witness scale and friction coefficient can reduce this effect. To view how allyships and rivalries are represented, we keep track of the strongest conflicting and strongest helping interpersonal forces for each character. When examining the curves of the strongest rivalries and the strongest allies, we found the following. The strongest allied characters followed similar shaped curves, whereas for rival characters, the curve would be mirrored. Consider the example shown here. In this section, the main rivals were Robinia and Feldspar, and the friendships varied between Ophelia, Dracena, and Robinia. In this small section of the story, Feldspar, whose ideal world is a boisterous high-energy one, is interacting with a number of calm characters, mainly Ophelia, Robinia, and Pollonia. There is a back and forth in the actions, with the characters specifically trying to speak calmly with Feldspar, who responds with high energy and more drinking. The conflicts occurring, though not well represented by the text, make clear patterns on the conflict curve. We can see that the rivals Feldspar and Robinia have roughly inverse conflict curves, and each character's actions not only reduces their own conflict, but always at the expense of the other character. At the same time, the allied characters often have curves that match each other, since in this case, neither character is aiming to cause any conflict to the other character. These inversions and mirroring can be analyzed at different points in the narrative simulation to understand the varying rivalries and friendships that are occurring. Through the experiments, we found the force dynamic model is able to show sophisticated behavior, creating regular conflict structures over time without the use of artificial systems, internal memory, or modeling of interpersonal relationships. The simplicity of this model and its results presents an alternate to many traditional emergent narrative approaches, focusing instead on the implicit behavior of a simple set of rules, and how this can be geared towards specific results.